I'm going to talk about some material from Lecture 14 today. As always, watching videos is no substitute for reading the book and notes. Okay, this is rather a long lecture, and that is because it has rather a lot to do. The first thing we got to do is try to give you some idea of what we mean by the probability distribution for a continuous random variable. So let's let x be some random variable. Right? So in the background there's some experiment going on, and the experiment is tried over and over again, and each time the experiment is done there's an outcome, and the value of x is set depending on that outcome. We're going to think of x as having a whole lot of possible data values. So here's the x-axis, and we're just going to put down a bunch of data values for this random variable x. And I'm going to draw them in a way I often do, and that is that most of the values are going to kind of be toward the middle, right near the mean, with only a few out near the ends. Okay. Now, before I go further, I want to talk about what we're interested in. We're interested in here the probability that the value of x is in a given interval. Remember, the value of x is set according to how the experiment turns out, and some outcomes in some regions, in some intervals, are more likely than those in other intervals. If you were to pick this interval right here, there are a lot more possible values of x in there than there are in an interval over here of the same size, right, but farther away from the middle there. So you would say that it's much more likely that the value of x is in this interval than it is in this interval. Okay, so what we're going to do here is we're going to construct a picture of the probability distribution of x in a kind of new way. It's going to look an awful lot like a relative frequency histogram, and in fact there's a way of thinking of it as such a thing. But it's probably easier just to construct it from scratch in this way. What we're going to do is we're going to use bars, and the bars are going to touch and so on, just like frequency histograms, relative frequency histograms. We're going to insist that the bars all be the same width. Okay, so I'm just marking off what are supposed to be equal widths here. Okay. But we're going to adjust the heights of the bars so that the probability that the value of x is in any of these intervals is equal to the area of the bar. So here you can see there are very few values of x in that interval, and so it's very unlikely that we would see one there. If the experiment were performed, the value of x is unlikely to end up down here, so you would expect the bar to be very low, right, so that the area was small. Here, the area of the bar needs to be higher, needs to be larger, so the bar would be higher. And here, probably about the same. Here, a little higher. Here, it would shoot way up. Right? Lots and lots of data points in there. This one, maybe not quite as high, and then we're back to very, very low ones again. Right? So now, again, the probability of finding a value of x in any of these intervals is equal to the area of the bar over that interval. Now, two things about that. First of all, suppose I were to pick some interval that was underneath two bars, then I could find the probability, right, if this is a point A and this is a point B, then the probability that the value of x is between A and B, which we write this way, right? The probability that the value of x is in this interval is just the sum of the areas of the bars over that interval AB. It would just be the sum of the areas of these two bars. The other thing to notice here is that if you sum up the areas of all these bars, well, that's the probability of finding a value of x here or here or here, or in other words, of finding a value of x somewhere. But the value of x has to be somewhere, so the sum of the areas of all the bars is 1. Okay, those two properties I'm gonna talk on at you for a good 5 or 10 minutes now about this, refining this idea. But these are the two important things, and they're going to persist all the way through right to the discussion of the probability distribution of a continuous random variable. They are the essential two things that we need to be aware of. Okay, let me show you a picture, a computer-generated picture that's considerably nicer than the one we just saw. Right. Let's see if I can get this in focus better. Good. Maybe we could think about this as being the experiment here is to pick a box of beet seeds. Good Lord, I can't seem to write. At random. Right? Now, beet seeds are very tiny, and boxes of them are filled by weight, not by counting out seeds, and so the number of seeds in each box is going to vary quite a lot. Right? You can see here the mean number is 1600. Right? That's the mean. But there's considerable variation. You're going to find boxes with 1300 and boxes out here with 2000 or whatever. And this picture, these bars here, these bars were constructed exactly the same way as the ones I just did by hand. That is to say, if you take a look at any one of these tiny little intervals here, it's going to have the probability that if you pick a box at random, the probability that the number of seeds in that box is in that little tiny interval is equal to the area of the bar over that interval. Right? So if we let x be the random variable that is the number of seeds in the box, right, the randomly chosen box, then the probability that the value of x is in some little interval here is equal to the area of the bar over that interval. And here are the two fundamental things that we need to know. First, so if you take any interval, like this one, let's say it's an interval so that the bars fill it out exactly, right? Then you can find the probability that the number of seeds in a box, that is the value of x, is in this interval by adding up the probability that it's in this little interval and this one and this one and this one and so on. In other words, you can add up the areas of all the bars that sit over this larger interval here. Okay. So that's one of them, right? One of the things. And the other interesting thing is if you add up the areas of all the bars, again, that's just the probability of finding the value of x somewhere among its possible values. And of course, again, that just has to be 1. The sum of the areas of all the bars is just 1. Okay, let me push this just a teeny bit further and point out that we don't really need the bars at all. What we need is this curve. I'm going to call it a curve. It's pretty jagged, but we can still call it a curve. What we need is this curve that's made up of the tops of the bars. As long as we have that, right, if we know how high this point is and this one, we can find these areas. And given that what we're interested in, right, we'd be interested here in the probability that x is between 1300 and 1400, right? That x, the value of x is in this interval. Well, all that is the shaded area. If we could find this shaded area, it doesn't matter how we find it, then we would have this probability. And if we have this curve that's made up of the bar tops, bar tops here, we can find this area because we know how high this is at every point. Okay, it's probably obvious to you that the way we're going to go from here to the probability distribution for a continuous random variable is to just use more and more of these bars and make them thinner and thinner. As you do that, of course you have to give up the idea of having only finitely many data points on the x-axis, because for a continuous random variable, any point on the x-axis can be a value of the random variable. Right? So you no longer have the luxury of counting the data points in an interval and dividing by the total number of data points. Instead, you have to just do it by areas. Right? If this is 1300 and this is 1400, right, and this is the x-axis, and we've gotten to this curve now by shrinking these bars down until they are infinitely thin. Each one is just now a vertical line. It's no longer possible to compute this area by computing the areas of bars and adding them up. But there is a way to do it. It's using calculus. And it is still true that the probability that x is in that interval, 1300 to 1400, right, it's still the shaded area. The area over the interval and under the curve. It's still also the case that the total area under the curve and over the x-axis, of course, is 1. Right? Because again, it's just going to be, right, if you relax down to any finite number of bars, that's going to be true. The probability of that x takes on some value on the x-axis is 1. And that's all that total area really is. There's one more consequence, and that is, suppose let's say this is 1500 here. Suppose you wanted to talk about the probability that x was actually equal to 1500. Well, that would be the width of this bar. And the width of that bar, the area of this bar. And the area of that bar is 0, because it has no width. Right? And that's going to be true for any continuous random variable. The probability that a continuous random variable takes on any particular value is going to be 1. Is going to be 0. The only thing that's interesting here is not to ask, as you do in the discrete cases, whether the random variable takes on a particular value. The only interesting question to ask is whether the value of the random variable is in some interval. And that is just going to be equal to an area under some curve and over the interval. Okay, let me say a few more words about this. A function, any function, a function, let's call it f of x, can be called a probability density function which is nearly always abbreviated to PDF. If two things are true about it. First of all, the graph of f never goes below the x-axis. Right? So f of x could be 0 in some cases, but it can never be a negative number. The graph is always entirely above the x-axis, or at worst, touching it. And secondly, the total area under the graph of f is 1. Right? Those are two qualities that the curves that we were just using had. Right? The graphs were always above the x-axis, or at worst touching the x-axis, and the total area under them is 1. Well, once you have that, once you have this definition of a probability density function, you can define, right? You can define the probability distribution of a continuous random variable. So let's let x be a continuous random variable. We'll abbreviate RV here. Okay. The probability distribution of x is an assignment of probabilities to intervals on the x-axis using a probability density function, right? That kind of function we just talked about there, right? Where the probability that A is less than or equal to X is less than or equal to B, right? That's the probability that the value of X is in some interval AB is equal to the area over the interval AB and under the graph, heavens to Betsy, graph of F. That's pretty much exactly what we've been doing. Right? If you had a picture very much like the ones we've been drawing, picture looks like this maybe. Right? This would be the PDF of some random variable x. This is the x-axis, and you want to know the probability that the value of x is between a and b in that interval right there. And what you need to do is to calculate this area that is over the interval AB and underneath the graph of the PDF. Right? This little area right here. Exactly what we've been doing. The big difference will be that we need help in calculating areas under continuous curves. If we don't know calculus, then the only thing we can do is to use a calculator. In this course, we will only see two families of continuous distributions, of which the normal family is the most important. That's what we'll talk about mostly today. And your calculator knows how to find areas under curves in those two big families of curves without any trouble. So that's what we will always do. We won't need calculus because we have a calculator. The most important distribution, family of distributions in statistics is normal distributions. And that's going to be our major focus in this course. Let me show you a picture. Here's a picture of the PDF of the normal distribution. It's pretty much what I've just been drawing, right? And you've been seeing printed. I need to point out a bunch of features about this, because this is going to be very important in your lives for a short time, for the rest of this semester. First of all, the mean of this distribution is this right here, this number mu. These are usually written in terms of population values, right? Population parameters, mu and sigma, not x bar and s, so they could be. This has mean mu. This particular normal distribution has mean mu. That's the number right under the highest point of the distribution. The distribution is completely symmetrical about this number mu. Now, that is to say, if you drew a vertical line through mu and the highest point on the curve and folded the paper in half along that line, the two parts of the curve would match up exactly. The standard deviation here is sigma, and sigma, how far sigma is from mu, controls how wide or narrow this curve is, and that's you get different normal curves for each choice of mean and standard deviation. I'll talk about that a little more in a little while. In this picture, if you start at the mean and walk to the right here, one standard deviation, you get to mu plus sigma. If you walked over another one, you'd get to mu plus 2 sigma, and then mu plus 3 sigma, and so on. Right? You can see that this stops at about mu plus 3.5 sigmas, and the same thing in the other direction. The total area under the curve is 1 because the total area under any PDF is 1. Right? We defined a probability density function not long ago, and one of the things about such a thing is that the area underneath it has to be 1. These points right here, if you go down to the x-axis, start at the mean and walk left 1 standard deviation, and then go up to the curve, you get to this point right here, which is called an inflection point of the curve. And the same thing happens if you walk right 1 standard deviation along the axis, and go up to the curve, you get to the other inflection point. Now, you're not going to have to find inflection points or anything. In fact, the only reason for me to tell you about them is because knowing about them, knowing actually what they are, what they say about the shape of the curve, and the fact that they occur one standard deviation from the mean in each direction helps you to draw normal curves better. And in order to learn this material, you have to draw hundreds of normal curves. You have to draw at least one normal curve for almost every problem you do that involves the normal distributions. Right? For quite a long time. There's no other way to learn the material. I have known instructors who would not accept assignments from students if they did not have curves drawn for every single problem. It is really that important. Keep drawing them until you're sick and tired of it, and then keep drawing them a little longer. Okay, what is an inflection point? First of all, probably the easiest way to tell you is if you think of this as a hill. Right? So I'm riding my bicycle, coming from left, moving toward the right. I'm going to hit this hill here. And at first the hill is not very steep at all. It's pretty flat, right? But as I go on, it gets steeper and steeper and steeper, and it's getting really steep. I'd actually fall off my bike long before I got to here, but it gets steeper and steeper and steeper. But at some point, it has to stop getting steeper because up here it's going to be flat again. Right? It can't get steeper forever, or it would never flatten out like this. So it's going to get steeper and steeper and steeper right up to this inflection point, and then it's going to get less and less steep until it gets to here. And then going down the other way, it gets steeper and steeper and steeper, just downhill, until it hits the inflection point, and then it starts flattening out again. Right? The inflection points are where the curve changes shape from being kind of cupped upward, right, where it would catch water, to being cupped downward where it would shed water. And knowing that that happens over the mean plus or minus one standard deviation just helps you to draw curves better. Okay, values of the random variable, or if you need to think about them that way, data values are along the x-axis here, of course. We can say what the y values are on the curve, but we don't need them in this class, and so we're just going to leave them out. They're unimportant for anything we do in here. The normal curve, as is required of a PDF, the normal curve never becomes negative. In fact, the normal curve never even touches the x-axis. It pretty quickly comes down so close to it that you can't see the difference in a picture. But in fact, there's always a little distance, some tiny little distance between the axis and the curve. Another thing is that almost all of the area under the curve, of course there's area, anywhere the curve is above the x-axis there's going to be area, so there's area as far out to the right as you wish to go and as far out to the left. But the area is so tiny that it's usually not important. In fact, 99.95% of the area is between 3.5 standard deviations to the left of the mean and 3.5 standard deviations to the right. Okay? This little interval right here, 7 standard deviations wide, contains 99.95% of the area under the normal curve. All right, we'll talk more about the standard deviation controlling the width and height of the central hump of the curve in a second. But first, can't see that. But first, here's the notation we'll use for this. Let me read this to you. It's important that you be able to understand this because problems will use it without explaining it. This is how you read this. The random variable x is normally distributed with mean mu and standard deviation sigma. Okay? The random variable x is normally distributed with mean mu and standard deviation sigma. If you look in other books, you may see this used slightly differently, but for us, it'll always mean exactly that. Okay? One more note about this. I keep talking about the mean and the standard deviation, and I never say anything else about normal curves, and that is because once you know the mean and standard deviation of a normal curve, you know everything about it. There's an actual formula out there, and the only things you have to put into it are the mean and standard deviation, and then you will get every point on the curve. So once you know the mean and standard deviation, you know everything about the normal curve. You don't need to know anything beyond that. All right, I'll talk about the influence of the standard deviation on the shape of the curve. Well, let's talk about the mean first, because that's a lot simpler. They're both pretty simple. Okay. But let's just look at an x-axis here, two copies of the same x-axis. Let's just draw a normal curve here, and let's say its mean is 10 and its standard deviation is 2, so this might be 12 and this might be 8, something like that. Okay? If I change the mean, so if I were going to write this in our notation, this would be n of 10, 2. That is normal distribution. This is the normal curve for mean 10, standard deviation 2. If I change the mean without changing the standard deviation, then the shape of the curve doesn't change, only its position on the x-axis. Right? So here's 10 over here, right, and 8 and 12. But let's go ahead and change the mean to 16. Now 16 is going to be out here somewhere, 16. And so this is going to look like this. Right? Oh, I didn't draw it too close to that one. But it would look exactly the same. Okay? And this would be 14 and this would be 18. It would look exactly the same as this curve. It would look as though you took this curve and slid it across the axis to get the new one. Changing the mean just changes the location of the curve without changing its shape. What happens if you change the standard deviation? Well, so again, x-axis, and here's the mean. Oh, I'm going to use this one again. And let's do this. So we'll make this n of 10, 2 again. Standard deviation 2. So here's 12, there's 8. All right. Now what happens if I change to standard deviation 1? Well, here's one way to think about it. If I change to standard deviation 1, that would be like taking the two inflection points here and pushing them closer together so that they were over 11 and 9. Right? There's 9 and there's 11. And so what I would get is I would get a higher and narrower curve. I don't draw too well, but there you go. Right? Same mean. I haven't changed the mean. This would be the normal curve with mean 10 and standard deviation 1. Right? And that's what making the standard deviation smaller does. Right? The total area under the curve has to be 1. So if I think of pushing these two x values under the inflection points closer together, what has to happen is the curve has to get taller and narrower. And similarly, if you use a larger standard deviation, here's a prettier picture. This is all of these curves have mean 0. This one right here in the middle here, this one has standard deviation 1. Right? And here's the one with standard deviation 1/2. Right? You can see the inflection points are, well, plus or minus a half. Hard for me to draw in there. Right? It's like taking this one with standard deviation 1 and squishing it. Right? The total area has to be the same, and what you get is a taller, narrower curve. Likewise, if you spread out the standard deviation, if you make it larger, then it's like dragging these points apart, which will make the curve lower and flatter. The central hump gets lower and fatter if you use a larger standard deviation. If you think of these normal distributions as applying to discrete data, then if you had something like this, I don't know, let's say this is 0, then you got a bunch of data points here, and they've got to be normally distributed. So this will take me a second. Right? Got to have more of them near the middle. Okay. Well, if this is the normal curve with mean 0 and standard deviation 1, then the normal curve with mean 0 and standard deviation 1/2, that would have to be for a different kind of data set. Sorry, I'll try to make that visible. There we go. That would have to be for a data set, right? Same mean, 0, but the data would be much more bunched up near the middle because its standard deviation is smaller. It's half the size. Right? However spread out this is, remember, standard deviation, you can think of it as being the average deviation from the mean of a data point. The standard deviation here is smaller, so the average distance between the mean and a data point is smaller. Right? So you should get a much smaller, a narrower and taller curve. Okay. One more topic. When we do use normal distributions to talk about data sets, which often we do, no data set is exactly normal, but they can be very, very close. And even if they're only approximately normal, a lot can be done with them. A lot can be done. We can find out a lot about them using the normal distribution. One of the things that we know is this thing called the empirical rule. And this is, you can see, this is for normally distributed data, right, where you think of having actual data that is approximately normally distributed. And what the empirical rule says is about 68% of that data will lie within one standard deviation of the mean of the data. About 95% will lie within two standard deviations, and nearly all of it, 99.7%, will lie within three standard deviations. Okay? In fact, in many real data sets, almost all of it lies within two standard deviations. But in any case, here's a picture of that. And here's the normal distribution for our data. Our data is, of course, these values along the x-axis here. And you can see this is drawn in using x bar and s rather than mu and sigma, because this is for sample data. X bar, of course, is the mean. If you go out one standard deviation to the left, one standard deviation to the right, this interval right here, 68% of the area under the curve is over that interval, which means 68% of the data will be in this interval, that is within one standard deviation of the mean. Similarly, 95% will be within two standard deviations of the mean, and 99.7% within three. Okay. So let's use this to do a problem. So here's an empirical rule problem. The number of bristles on the abdomen of a certain species of fly is normally distributed with a mean of 38 and a standard deviation of 5. On the normal curve shown, mark the mean, so on. Okay, so let's do that. First of all, the mean is the number right under the highest point, so this is going to be 38. The standard deviation is 5, and I'm going to put the standard, move over one standard deviation here, and this would be 38 plus 5, or 43, and then this would be 48. Similarly, this way, this will be 28, right? 38 minus 5 down to the next, no, it will not be. It will be 33, and then this one will be 28, right? Mean minus one standard deviation, mean minus 2, and so forth. And this could be 23. All right, first question, very easy one. About what percentage of these flies have between 33 and 43 bristles on their abdomen? So that would be between here and here. In other words, in this little interval right here. Now this is the interval from the mean minus one standard deviation to the mean plus one standard deviation. And the empirical rule says that that interval there contains just about 68% of the data. Okay, next one's a little harder, got to think a little more. About what percentage of these flies have between 28 and 33 bristles on their abdomens? Now if I go up to the picture here, that would be the percentage that fall in this interval right here. Well, how are we going to calculate that? Probably the easiest way to do it is to draw some pictures and subtract some areas. So let's start with this. We know that, let's see, this is 38, 33, 28, 43, 48. We know that this interval here contains 68%, right? 68%. And we know that this interval here, the interval from 28 to 48, so from the mean minus 2 standard deviations to the mean plus 2 standard deviations, this interval contains 95%. So that means And let's redraw here. $28, $33, $38. Okay, so that means that this interval plus this interval right here, right, these two intervals together, right, have to have 95% minus 68%. If you take the whole thing here, you subtract out that 68%, right? So shaded intervals, they have about 95% minus 68%, or 27%. But remember, everything here is completely symmetric about this vertical line through the mean. So this interval and this interval are exactly the same size. And the probability, you can see the probability here, this area over this interval. So this says that the percentage with between 28 and 33 bristles is about 27/2, or 13.5%. Okay, and the last part here asks, if a fly of this species is chosen at random, what's the probability that it'll have between 28 and 33 bristles on its abdomen? Well, about 13.5% of the flies have between 28 and 33 bristles, so you would say that the probability, if x were a random variable that counted the number of bristles, you might say this. The probability that the number of bristles between 28 and 33 would be about 0.135, 13.5%. All right, it's been a long lecture, but that's it.